Tonight, we're going to explore something that sounds deceptively simple, yet it's one of the most profound ideas in all of science. A light year. You've probably heard the term many times. It sounds familiar, scientific, routine. But understanding what a light year truly is, grasping its scale and what it represents, changes how you see the universe. Because a light year is not just a number, it's a doorway into cosmic perspective. It is a distance so immense, so unlike anything in our everyday lives, that it almost breaks the brain. And yet, it's essential. Without it, we couldn't make sense of the universe at all. Let's start with something familiar. Distance. You understand distance in your everyday life. The grocery store is a few kilometers away. A trip to another city might be a few hundred kilometers. A vacation abroad might span a few thousand. A kilometer is a distance you can walk in about 10 to 12 minutes. It's something you feel. Your legs know it. Your sense of time knows it. If someone tells you the store is 5 kilometers away, you instantly know what that means. You can picture the walk or the drive. You know what to expect. You can feel that distance in your body. We've evolved to understand distances like that. Human distances. The distance to food, to shelter, to danger. The distance we can walk in a day. The distance we can see with our own eyes. Even larger numbers can still feel tangible. New York to Los Angeles? About 4,500 kilometers. A 5-hour flight. Long but manageable. The Earth's circumference? About 40,000 kilometers. Big, but explorers have traveled that. Planes can circle the planet in less than 2 days. It's impressive, but not beyond comprehension. These distances, even when large, still connect to us somehow. They fit into our minds. They can be traveled. They can be planned for. But at a certain point, distance begins to lose meaning. When you look up at the moon, you're seeing something that is about 384,000 kilometers away. Already that number feels strange. Abstract. It's not something you could drive to or fly to in a commercial plane. It's a destination only a handful of humans have ever reached, and only with enormous effort. The Apollo missions traveled at speeds of over 39,000 kilometers per hour. Even at that incredible velocity, it took the astronauts about 3 days to reach the moon. 3 days, at rocket speed, through empty space. No landmarks, no highways, no stops, just pure, unimaginable distance. And yet, the moon is close. You can see it with your eyes. With binoculars, you can spot craters and ridges. It feels like part of our world. But the journey to it, just that short leap into space, already requires technology most people will never touch. Then we go further. The sun, our star, the source of light and heat for all life on Earth, is about 150 million kilometers away. Let that number sit for a moment. 150 million kilometers. And at that scale, something breaks. Your mind resists it. What does that distance feel like? Can you imagine walking it, driving it, even flying it? No, because you've never experienced anything remotely close. If you tried to drive to the sun at 100 kilometers per hour, a decent highway speed, it would take you over 170 years. You'd need generations of drivers. It becomes absurd. Even the fastest spacecraft humans have built, the Parker Solar Probe, moves at 192 kilometers per second when near the sun. That's nearly 700,000 kilometers per hour. And still, it takes months to make the journey. This is where kilometers fail us. The numbers become too big. They don't connect to anything we know. They become just numbers, strings of digits with no anchor in experience. And this is why astronomers needed something else. Not to sound smart, not to complicate things, but because human-scaled measurements, meters, kilometers, simply stop working when we step into the universe. They needed a measurement that made sense at scale. That could speak the language of stars. That could measure the cosmos. They needed the light year. And before we understand what a light year is, we have to understand why light is so special. Light is not just another thing in the universe. It is fundamental. Light is the fastest thing that exists. Nothing travels faster. Nothing even comes close. This isn't a technological limitation. It's not something we just haven't solved yet. It's a deep law of reality itself. Light travels at about 300,000 kilometers every second. Pause on that for a moment. 300,000 kilometers in a single second. In 1 second, light can circle the Earth more than 7 times. In 1 second, it could travel from New York to Los Angeles and back dozens of times. In the time it takes you to blink, light has already crossed continents. Nothing in your everyday life prepares you for that speed. The fastest thing most of us ever experience is an airplane. A jet moves at roughly 900 kilometers per hour. Light moves over 1 million times faster. Because our rooms are small and our lives are local, light feels instant. You flip a light switch and the room fills with light immediately. But it isn't instant. The light still travels. It just travels so fast that your brain can't notice the delay. Even across the room, light takes time. That time is just measured in billionths of a second. But when distances grow larger, that time becomes noticeable. When you see the sun in the sky, you are not seeing it as it is right now. You are seeing it as it was 8 minutes and 20 seconds ago. If the sun were to suddenly disappear, if it somehow ceased to exist at this very moment, we would continue seeing it shining peacefully in the sky for over 8 minutes. The light would still be on its way. The event would have already happened, but we wouldn't know yet. This means something profound. Light carries information, and information takes time to travel. When you look at the moon, you're seeing it as it was about 3 seconds ago. That delay is small, but it's real. When astronauts walked on the moon and spoke to mission control on Earth, there was always a pause in the conversation. They would speak, and mission control would respond more than a second later. Then another pause before the reply came back. That gap exists because radio waves travel at the speed of light, and even light needs time to cross space. For most of human history, people assumed light traveled instantly. It seemed obvious. You open your eyes, and the world appears immediately. But in the late 1600s, a Danish astronomer named Ole Rømer noticed something strange. He was observing the moons of Jupiter and tracking when they disappeared behind the planet. Sometimes the eclipses happened earlier than expected, sometimes later. The pattern wasn't random. When Earth was closer to Jupiter, the eclipses appeared sooner. When Earth was farther away, they appeared later. Rømer realized what was happening. Light wasn't instant. It took time to travel across space. His measurements weren't perfect, but the conclusion was revolutionary. Light has a finite speed. Centuries later, we would measure that speed with extraordinary precision, using lasers, atomic clocks, carefully controlled experiments. And what we found was astonishing. The speed of light is not just fast, it is constant, no matter where you are in the universe, no matter how fast you're moving. Light always travels at the same speed. If you are standing still and shine a flashlight, the light moves at 300,000 kilometers per second. If you are moving at half the speed of light and shine a flashlight, the light still moves at 300,000 kilometers per second. This breaks our intuition completely. In everyday life, speeds add together. If you throw a ball forward from a moving train, someone standing on the ground sees the ball moving faster than you threw it. But light doesn't behave that way. To preserve the constant speed of light, the universe does something extraordinary. Space and time themselves adjust. As objects move faster, time slows down for them relative to stationary observers. Distances in the direction of motion contract. These are not illusions. They are real physical effects. This is time dilation, and it has been measured over and over again. Particles traveling near light speed live longer than identical particles at rest. GPS satellites must adjust their clocks to account for time dilation, or navigation would drift by kilometers every day. The fact that GPS works is proof that time itself is flexible. Light defines the structure of space-time, and because light has a fixed speed, it gives us a natural ruler for the universe, which brings us back to the light year. A light year is not a measure of time. Despite its name, it has nothing to do with how long something lasts. A light year is a distance. It is the distance light travels in 1 year. To calculate it, we start with the speed of light, about 300,000 kilometers every second. Then we count 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. Multiply it all together. The result is staggering. A light year is approximately 9.46 trillion kilometers. Trillion. Not million. Not billion. Trillion. That number is so large that it almost has no meaning on its own. It needs context. And to understand it, we first need to understand what a trillion actually is. Let's talk about the word trillion. We hear it thrown around in news stories, government budgets, national debts, astronomical distances. But few people ever stop to feel what a trillion really means. So let's build up to it. A million is 1,000 thousands. If you saved $1 every single day, it would take you about 2,740 years to save $1 million. That's older than most civilizations. A billion is 1,000 millions. If you saved $1 every second, it would still take over 31 years to save $1 billion. That's a generation. But a trillion? A trillion is 1,000 billions. If you counted one number every second, non-stop, no sleeping, no eating, just counting, it would take you over 31,700 years to reach a trillion. That's longer than all of recorded human history. And that is the scale we're talking about when we say 1 light year is 9.46 trillion kilometers. 9 trillion, 460 billion kilometers. Each one of those kilometers is a real distance, about the length of a 10-minute walk. And there are trillions of them in a single light year. We can write that number down. We can include it in equations. We can simulate it with computers. But to feel that distance, to truly grasp what it means, that's something else entirely. Our brains did not evolve to comprehend such scales. We evolved to understand the distance to the next hill, to the next water source, to the place we could reach in a day. The scale of the universe is not just big. It is incomprehensibly big. Let's take it step by step. 1 light second is 300,000 kilometers. That's nearly the distance from Earth to the Moon. In 1 second, light can leave Earth, reach the Moon, and get 3/4 of the way back. 1 light minute is 18 million kilometers. The Sun is about 8 light minutes away, so when you see the Sun, you're looking 8 minutes into the past. 1 light hour is over 1 billion kilometers. That's roughly the distance to Saturn when it's closest to Earth. 1 light day? Over 25 billion kilometers. And here's where things get cosmic. The most distant human-made object, Voyager 1, launched in 1977, has been traveling through space for nearly 50 years. It's now about 1 light day away. 1 light day, decades of travel, tens of thousands of kilometers per hour. All of it. And it's still within a single light day. 1 light week is about 181 billion kilometers. Now we're far beyond the planets, out in the void between stars. 1 light month? About 778 billion kilometers. At this distance, even our entire solar system becomes small, just a point of light around a medium-sized star. And 1 light year is 9.46 trillion kilometers. It's the distance that light travels in 1 year, moving at 300,000 kilometers every second, non-stop, for 365 days straight. And this is what astronomers use to measure distances between stars, because nothing else makes sense anymore. To give you an idea, the nearest star to the Sun is Proxima Centauri. It is about 4.24 light-years away. That's roughly 40 trillion kilometers. Even if you could travel at the speed of light, which we can't, it would still take you over 4 years to get there. With our fastest spacecraft, the Parker Solar Probe, it would take over 6,800 years. Let that sink in. If humans had launched a mission to Proxima Centauri back when the first pyramids were being built, that spacecraft still wouldn't have arrived yet. And wouldn't for thousands more years. This is why light years are not just numbers. They represent a barrier, a boundary of scale that separates us from the stars. And it's not just about distance. Because light takes time to travel, when we look into space, we're also looking into the past. The farther away an object is, the older the light we see from it. When you look at Sirius, the brightest star in the night sky, you're seeing it as it was 8.6 years ago. When you look at Vega, you're seeing light that left 25 years ago. Betelgeuse? About 550 years ago. The light you see tonight began its journey during the Renaissance, before the invention of the telescope. And that's just nearby. When we look at distant galaxies, we are seeing them millions or billions of years in the past. Some of the galaxies we observe through telescopes no longer exist as we see them now. They may have merged, exploded, faded. But the light they emitted eons ago is still arriving, still telling us their story. Because light carries history. It is a time capsule, a record of the universe, still traveling long after the moment it was born. And this is why the light year is more than just a unit of measurement. It is a measure of time as much as distance. It links where something is, to when we're seeing it. In the universe, space and time are not separate. They are woven together, and light is the thread that ties them. Let's go even farther. The Milky Way, our home galaxy, is about 100,000 light-years across. That means, even traveling at the speed of light, it would take you 100,000 years to cross it from one side to the other. Let's break that down. If you started a journey today, moving at the fastest speed the universe allows, you would arrive at the opposite end of the galaxy sometime in the year 102,026. That's 100 millennia. Longer than all of recorded human history, several times over. Now step back even further. The Andromeda Galaxy, the nearest large galaxy to ours, is about 2.5 million light-years away. So the light we see from Andromeda tonight began its journey during the time of early humans, before the invention of agriculture, before language as we know it. It's possible that civilizations have risen and fallen in that galaxy, entire histories written and erased. And we won't know about any of it for millions of years, if ever. And what about the observable universe? That stretches out to a distance of about 46.5 billion light-years in every direction. Why so much larger than 13.8 billion, the age of the universe? Because space itself is expanding. As light travels toward us, the fabric of space stretches, pulling galaxies farther away even as their ancient light races toward us. This means some parts of the universe are so far away that their light will never reach us, no matter how long we wait. They exist, but they are forever beyond our horizon. And the number of stars? Estimates suggest there are around 200 billion trillion stars in the observable universe. That's a 2 followed by 23 zeros, each one potentially hosting its own planets, its own systems, its own chance at life. And yet, despite this abundance, the universe feels quiet. We've sent radio waves into space for about a century. Our signals now form a sphere about 100 light-years wide. But even that tiny bubble hasn't reached most of the nearby stars. And by the time it does, the signals will be faint, almost indistinguishable from the background hum of the universe. So when people ask, why haven't we heard from anyone else? Part of the answer may simply be, it's too soon, or it's too far. The light year, in this sense, becomes a wall. Not one we can break, but one we can only stare across. The more we understand it, the more we realize what it means to be alone, at least for now. But isolation doesn't mean insignificance, because in all this vastness, in all this silence, we are here, on a small world, orbiting a single star. And somehow, from that fragile place, we have built tools that allow us to measure the cosmos. We can look at stars thousands of light years away and know how far they are. We can decode their chemistry. We can map their motions. We can detect the subtle pull of orbiting planets. And sometimes, we even find worlds that might be like ours. All of this because we understand the speed of light. Because we invented the light year. That small unit, 946 trillion kilometers, became our passport to understanding the universe. It gives us perspective. That reminds us, your worries, your problems, your fears, they're real, they matter, but they are small, not unimportant, but temporary, local, because you, right now, are living on a planet in a solar system, in a galaxy, in a universe so immense that even light takes billions of years to cross it. And yet somehow, you can understand this. You can imagine it. That ability, more than any rocket or satellite or space telescope, is what truly connects us to the stars, because we are made of the same matter, forged in the same ancient explosions, bound by the same physical laws. We are the universe, becoming aware of itself. So tonight, when you look up at the night sky, remember what you're seeing. You're seeing across light years. You're seeing into the past. You're seeing the truth of scale and time and space. And in that vastness, as small as you are also extraordinary. Thank you for joining me on this journey through space and time. This is Zenth Lab, where wonder begins with perspective.